This case is analytical determination of the cam profile for an oscillating cylindrical follower. As in this case, the position for the cam profile can be derived with the use of instance centers. We have the follower displacement is given in the formula phi equal to f of theta. The follower rotates about the pivot E with the angular displacement of phi. To begin the procedure, we will give several main parameters for determining the cam profile. The base circle radius is RB. The radius of the cylinder follower is R0. The pivot distance is R1. And the distance from the follower pivot to the center of the cylindrical follower is R3. This slide shows you how to determine the coordinates of the cam profile. We locate the follower in the initial position and the general position. Point B is a contact point on the cam. We see the position of point B relative to the origin have the distance r and the angle gamma plus theta. So, we can represent the position of the contact point B in coordinates like this. For determining the coordinates of the contact point B, we need to calculate the magnitude of r and the angle gamma. These contact points will construct the cam profile for the cam angles from 0 degrees to 360 degrees. Again, we must invert the mechanism so that the follower appears to rotate about the cam. In the procedure, we assume the follower begins in its lowest position when the follower contacts the base circle of the cam in the initial position as shown in this figure. For this position, we need to determine the angle phi 0, which is the initial angle for the follower. From the triangle ACE, phi 0 can be computed using the law of cosines like this. To start the procedure, we need to locate the three instance centers I12, I13, and I23 for a system in the displaced position corresponding to theta. We can locate the instance centers I12 and I13 by inspection. I12 locates at the pin joint, and I13 is at the follower pivot. The instance center I23 locates at the intersection point of line I12 and I13, and the common normal at the cam contact point B. We label I12, I23, and I13 as A, D, and E respectively. The distance of line ID is B. By the definition of the instance centers, location D corresponds to the two coincident points on fixed to link 2D2, and the second fixed to link 3D3. The two coincident points have the same velocity relative to the frame. VD2 is equal to VD3. The magnitude of the velocity of D2 is given by omega 2 times B where omega 2 is the angular velocity of link 2. And the direction is perpendicular to the line through I12 and I13. The velocity of D3 is given by omega 3 times R1 plus B, where omega 3 is the angular velocity of the link 3. Let's look at omega 3. The angular velocity of link 3 can be written in terms of rotation angle. From the calculus chain rule, d∅ over dt is equal to d∅ over d theta times d theta over dt. So we have omega 3 is d∅ over d theta times omega 2. Therefore, Vd3 is equal to d∅ over d theta times omega 2 times R1 plus B, equating the velocity of the point D2 and D3 gives the relation. Then we get V like this. The vector r is the coordinates of the point on the cone profile. They can be computed with the end of the right triangle CFE and the polygon CFAB in this figure. From the right triangle CFE and the CFD, the angle lambda is given by this equation. From the right triangle AGB, we have the length of its side. Then we can get the magnitude of vector r like this, and get its direction gamma like this. Later, we will talk about the detail. From the right triangle BHC, we have length of its sides. B is equal to R0 times sine of lambda, and C is R0 times cosine of lambda. We can calculate the length of two sides D and E for the right triangle AGB. Then from the right triangle AGB, we have the length of its side D and E like this. And we get R and lambda. Therefore, we can get the coordinates of point B on the cone corresponding theta like this. The pressure angle indicated by epsilon in this figure. It is the angle between the velocity of point B3 and the normal line to the surface at the contact point. The direction for the velocity of point B3 is perpendicular to the line BE. The normal line to the surface at the contact point is the line BD. From the contact point to the instant center, I23. For the geometry in this figure, an expression for the pressure angle is like this, where the angle psi is unknown. We need to determine this angle. From the triangle BCE, we have sides R3 and R0. If we have the length of line VE, we can compute the angle psi using the law of cosines. From the triangle CDE, we can compute the angle theta. Based on knowing two of the internal angles and get theta like this. Then from the triangle BCE, two sides R3 and R0 and the angle theta are known. We can compute BE using the law of the cosines. Example 10.9 is to determine the cam profile for an oscillating roller follower. The rotation angles for the follower are given here. In this case, the cam rotates in the counterclockwise direction, so the variable SGN will be -1. This slide shows you 4 formulas for the follower in low dwell, rise interval, high dwell, and the return interval. The rise interval is with 3, 4, 5 polynomial motion during the cam rotation from 19 degrees to 118 degrees. And the return interval is with harmonic motion during the cam rotation from 217 degrees to 316 degrees. This case, the follower gets 0 pressure angle in the initial position. The angle ACE must be 19 degrees for the pressure angle to be 0 during the initial dwell. Therefore, from the right triangle ACE, we can compute R3 by this formula. Then we can compute the initial angle phi 0. This diagram shows cam follower system, the follower displacement, radius of curvature on the cam surface, and the pressure angle. Later, I will show you how to use Excel to determine this problem.